Good morning, students. Welcome to online video lecturing class. So today we'll start with the second model, that is mathematical modeling of physical systems. So in the previous model we studied about the types of the control systems, difference between open loop and closed loop control systems, and what are the requirements of the ideal control system, and what are the different types of controllers and their properties and their characteristics. So in this model, we'll study how to do the mathematical modeling of a physical system. So before moving with starting with the actual mathematical modeling of a physical system, first we'll try to recall some of the terms like Laplace transform and inverse Laplace transformation, which you already studied in your engineering mathematics. Okay, so to begin with, so first we'll try to understand what exactly this Laplace transform. So it is the information transformation technique relating the time functions to frequency dependent function of a complex variable. Okay. So for example, if you let the consider real function as f of t and the real variable as t, where t is greater than 0. So then we can write it as f of s is equal to L of, that means Laplace of f of t. You can write it as integration of 0 to infinity f of t into e raised to minus st into dt. So here this equation, this f of s is a Laplace transformation of this real function, that is f of t, and where this s is frequency dependent complex variable, which is defined as sigma plus j into omega, where this sigma is real part and omega is imaginary part. So you need to remember some of the basic Laplace transformation of the functions. For example, if the function is f of t, then the Laplace transformation of derivative of that function, that is d by dt of f of t, will be s into f of s, where the initial condition at t equal to 0. Similarly, it is L, that is Laplace transformation of d square divided by dt square of f of t will be s square into f of s. If the order is n, then we will get it as s raised to n into f of s. Now we will start with the mathematical model. So basically this mathematical model is the representation of a control system by the use of simple equation or a differential equation is called mathematical model of a control system. So if you take any physical system or physical model, for that model you can write the simple mathematical equation, or you can use the differential terms. So if you are able to write the differential equation for a given system, and if that equation contains all the variables which are going to happen in your system, then we can call those equations as the mathematical equation for that particular system. Just by using those equations, you can study the behavior of this system. For example, if there is a variable in your system, and if you are adopting that variable in your differential equation, just by altering the value of that variable in your equation, you will get the different result, that is different solution. So that solution should match with the actual output of the system. So that means it is exactly a replica of your actual system, but here you are theoretically you are writing in terms of differential equation. So those equations you can call it as mathematical model of a control system. So when you write the mathematical equation or when you make the mathematical model, now it is important to understand how to write the transfer function. So before beginning with that, we'll try to understand what exactly the concept of this transfer function. So here in this block diagram you can see this is a selected input, system parameters and output. So in system parameters, need to select the proper parameters to get the required output. So here the performance of a system can be expressed in terms of its output. Okay, because if you design or if you model any system, ultimately you are having one output. Okay, so it is meant for to give some certain output. So to get that output, you need to adopt some of the methods, or you need to give some of the variables in the system so that it can give you the desired output. So here the output is given by input, that is the initial commands which you are going to give the control system, then it is multiplied with effect of system parameters. Based on your input and based on your output, what all the actions has to be taken place in the system, those are known as effect of system parameters. So from this you will get the output. So now if you want to write the equation for effect of parameters, will be given by, it is a ratio of output by input. So mathematically, a function explaining the effect of a system parameters on input to produce output is called as transfer function. In general, you can call it as it is a ratio of output to input. Now moving further, so the basic definition is, mathematically it is defined as the ratio of Laplace transform of output, that is the response of the system, to the Laplace transform of the input, that is excitation or the driving function or whatever the input you are giving, that is under the assumption that all initial conditions are 0, that is at a time t equal to 0. So symbolically it can be represented as, for a system, R of t is the input and C of t is the output, and this is the system. So if you take the transfer function of the above system, you can rewrite it as R of s, and here system can be t of s and C of s. So from this, the transfer function of the system is given by output divided by input. So here in this figure they are just input and output. After applying the Laplace, will become C of s and R of s. So you can write the transfer function as C of s divided by R of s. If this transfer function T of s is the transfer function of a system, then we can write it as Laplace transformation of the output divided by Laplace transformation of the input. So So the writing the transfer function will helps us to understand the system behavior, because it will give you the mathematical model for all the system components and for the overall system. So the individual analysis of various components in our system can be possible if you have the proper transfer function approach. And as it uses the Laplace approach, it converts a time domain equation into simple algebraic equations, so which will be easy to analyze. And also it suggests the operational methods of expressing equations in which relate to output to the input. And the transfer function is expressed only as a function of complex variable s. It is not a function of real variable or time or any other variable. So that is used as the independent variable. So now let us try to understand how to write the transfer function of a mechanical system. So here basically the systems having translatory motion can be characterized by its displacement, linear velocity and linear acceleration. We have the Newton's law of motion that gives you the sum of the forces applied on a rigid body or a system must be equal to sum of the forces consumed to produce the displacement, velocity or linear acceleration on the system. So by using this Newton's second law, you can easily write the transfer function of the given system. So before starting with the actual problems, first we'll try to understand some of the components of your mechanical system which are having the translatory motion. So these are the main three elements involved in analysis of translatory motion. The first one is mass, second one is spring, and third one is friction. So mass, it is a property of a system itself which stores the kinetic energy of the translatory motion. So here in this figure, m is the mass and f of t is the applied force, and this x is the displacement which is occurring at in the direction of applied force. And here we are assuming that it is having zero friction. Okay, so for this, if you want to write the transfer function, you should know the output, right? So for here the output is the displacement of this mass and input is the force which are going to apply on this body. So force required for the same displacement is proportional to the acceleration here. So f of t, we can write it as mass into acceleration. So where the mass is m and acceleration, displacement is from x of t. So if you want to write in terms of acceleration, write it as d square x of t divided by dt square. So if you take the Laplace transform of this equation, you will get it as f of s equal to m into s square into x of s. So suppose there are two bodies which are rigidly connected and the force is applied on the mass m1 as shown in figure, then on m2. Here the two masses will have the same displacement because this connection is rigid here. So the rigid connection, whatever the displacement is having by mass m1, the same displacement will be for m2. Again here also we are considering it as zero friction. Then coming to the next element, that is spring. So it has a property to store the potential energy, and the force required to cause the displacement is proportional to net displacement in the spring. Whereas in case of mass, the force required to have this same displacement is proportional to the acceleration. So here it is proportional to the net displacement in the spring. So if you consider a spring K, where K is the spring constant, or you can say it as spring stiffness, and if you apply the f of t at this end, it will have the x of t, that is the displacement. And you can write the equation as f of t equal to k into x of t. Now if there are two masses which are connected by the spring, m1 and m2 are connected by a spring k, and f of t is applied on m1. So while looking at the mass element, there the connection was rigid, but here they are connected by the spring K. So now for this kind of a system, first you need to draw the free body diagram. So I will mark two nodes which are m1 and m2. The f of t is you are applying on m1. So here it will be having x1 of t as the displacement, and this m2 will be having x2 of t as the displacement. So now to cause the displacement on this m2, that is x of 2, the net displacement in the spring will be difference between those two, that is x1 minus x2 will be the net displacement which is occurring on the spring to give the displacement for the masses m1 and m2. And the opposing force, because spring always it opposes the motion or the displacement. So here you can write the equation as F surface spring, that is force required for the spring, is given by is equal to K into x1 of t minus x2 of t. If you take the Laplace transformation of this, will be F of s is equal to K into x1 of s minus x2 of s. Now moving to the third element, that is friction. Whenever there is a motion, we cannot avoid the friction, so there exists a motion. In some cases, we used to assume that it is having a zero friction, or there is no friction. But in reality, there will be a friction. So it may be between a moving element or fixed support, or between two moving surfaces. So the friction is generally shown by a dashpot or a damper in the mechanical system. So this is the symbolic representation of a dashpot or damper. So now let us consider a system with a support friction with a constant B. So here this B is the frictional constant. So as we have considered the same example while studying that mass as the element. So there we have taken it as zero friction, but here we'll have the friction. Okay. So the equivalent system for this one will be replaced this friction by this dashpot. So whatever the force you are going to apply on this F of t, that is on M, this will have the x of t as the displacement. Along with that, there will be some friction at the connecting surface of the mass and the surface. So always this friction will oppose the motion of the mass, and the opposing force for this motion is always proportional to the velocity of the mass. And you can write the equation as F frictional is equal to B into d by dt of x of t. So here, why it is d by dt of x of t? Because it is proportional to velocity. But in case of mass, it was proportional to acceleration, and in case of spring, it was proportional to the net displacement. So if you take the Laplace transformation of this equation, you get it as f of s equal to b into s into x of s. Similarly, if that damper or the dashpot is connected between the two masses, it is similar to the spring analysis, where the spring is connected between two masses. So only difference is, while writing the equation, you have to consider the proportional to its velocity, not to the displacement. So f of friction equal to b into d by dt of x1 of t minus d by dt of x2 of t. So if you take the Laplace transformation of this equation, you will get it as f of s equal to b into s x1 of s minus x2 of s. Now moving further, so now it is very important to draw the equivalent mechanical system. That means the given system may be of any type. That means it may have any type of the elements. But we need to convert that given system into a spring mass damper system. That means in your entire system, you should have only three elements. That is mass, spring and damper. Along with that, the displacements. So how to convert the given system into the equivalent mechanical system, which is having only spring, mass, damper. So these are the 5 steps you need to remember. So the very first step is, first you need to identify the displacements in the system. How many displacement elements are there? For example, if there are two masses, if they are connected by a spring or a dashpot, no doubt there will be two displacements, as you have seen already, x1 and x2. So those number of displacements you need to identify. Then the second one is identify the elements which are under the influence of different displacements. Because if you take the x1 is occurring on m1, so the m1 is related to x1. If x2 is happening on m2, m2 is related to x2. But if these two masses are connected by a spring or a dashpot, that spring or dashpot will have the combination of x1 and x2, right? So you need to identify the elements which are under the influence of both particular displacements. Then represent each displacement by a separate node. For example, if there are two displacements, first you have to mark two nodes. If there are three, you need to mark three nodes. Then fourth step is show all the elements in parallel under the respective nodes which are under the influence of respective displacements. For example, if m1 is having only x1, connect that m1 to x1. If m2 is having only x2, then connect that one to x2. Then the fifth step is elements causing the same change in the displacements will get connected in parallel between the respective nodes. For example, if the spring is connected between two masses, you need to show that spring between those two nodes which are represented by as x1 and x2. So these are some of the terms for an element connected to a node X and satisfactory stationary surface is mass, you can write it as m into d square divided by dt square of x. Friction is b into dx by dt, and spring as kx. So by considering this example, we'll try to analyze these 5 steps. So here it is a system which is having a damper B, then spring, then mass m, and here it is x of s, that is the displacement. So to write the equivalent mechanical system, the first step is you need to identify the number of displacements. So here we are having only one displacement, that is x. So mark that x, and it is then you need to identify the elements which are under the influence of that displacement. So here this, for example, is m is having the displacement of an amount x. Definitely this b and k are having the same amount of displacement because they are connected parallelly. So for that x, you need to attach m, k and b. So this is the equivalent mechanical system of this given system. Then so here you need to understand how to write the differential equation if the system is having mass, spring and dashpot. So while writing the differential equations, you need to remember this one. Force due to mass will be mass into acceleration. Force due to friction will be b into dx by dt. Force due to spring will be k into x. And you should remember all these 5 steps to draw the equivalent mechanical system. Okay, so these are some of the basic points which you need to understand to solve the problems. So in the next class, we'll try to solve some of the basic problems by following these definitions or the basic differential terms, and by using these 5 steps to draw the equivalent mechanical system. Okay, if you have any query, you can comment in a comment box. Thank you.